Hello everybody, this is again Dr. Sergey Sargasov, and I want to show us an interesting derivative and how to find it today. I was actually thinking about what are some derivatives that are seemingly basic, but they're not so basic. They seem basic, but they're actually not so basic. And so let me show you what I mean by that, like a calculus 1 type problem. All right, let's first remember what a derivative even is, okay? You can write, like, for example, f prime of x, right? We usually write that as derivative, meaning like differential of the function, okay, over the differential of the kind of the horizontal, the x, right? df dx, we can write that, like of x, right? And we can also say, what is that? So this is the limit, right, as h goes to 0, basically like a differential, right? The kind of the little, remember, the sum of the rectangles infinite amount of times, that, for example, gives you the area under the curve. And so, for example, the slope of the tangent line is when you're talking about what? When you're talking about that space between the 2 points is so small, right, that they're basically on the same point where it's the tangent line and at that location. And so this is delta h is that horizontal, delta h or dh, okay? Anyway, so we have that delta h. Let me make a little neater h. I just want to show you, just remember what a derivative even is, right? Because some people forget where the derivative comes from. Basically, it's one of the ways to define it is the definition of kind of, what is that slope of that tangent line. So this horizontal here, see that right there? It's very small to visualize. That's an h right there. Anyway, so limit as f of h, as h goes to 0, the function at the kind of the right point a little bit to the right there, right? See that little point I'm circling, okay? And the function value there, the y, basically the slope, y2 minus y1, which is f of x there, over just the x plus h over minus an x, which is just h is left at the bottom, right? Anyway, that is the derivative definition that we're usually used to, and we can use it to find a lot of things. In fact, any derivative can come or can be found in some way. If it's found, if it is something we can find, it comes from, you can come back to this formula and find it from here, okay? Anyway, I want to remind you just some basic derivatives. For example, the power rule, before we continue with kind of interesting what I was going to show you. Power rule, that's if you have like derivative of, let's say, some x to some power n, that's going to give you what? And you can do this definition, it will give you that. There's a binomial theorem involved there, okay? But it's going to give you n, the power becomes a coefficient, and then x to the power goes down by 1. Okay, that's an important thing. For example, x squared goes to 2x to the first power, 2x. X cubed goes to 3x squared, and so on, okay? Power rule, now let me do the e to the x. What is derivative special? This is exponential. And this is tricky to prove because you have to use some tricks. And I can do this, but we've done it in other lessons. I want to show you kind of more what I was going for in this little lecture here. So special exponential, yeah, you have to know that, for example, derivative of e to the x, right? The natural, the Euler number, not Euler. That's not the way you say his name. So this is Euler number and spelled like this. So okay, German, what is it? Name, right? So Euler number, and this guy is probably the mathematician that I think is like the most prolific. If nothing else, even if we cannot say he's the greatest mathematician, which I do think he is, this is my kind of favorite guy here. A lot of E everywhere, complex analysis comes from him, number theory, probability, a lot of things he did. Even calculus he touched upon in some ways, okay, before like Isaac Newton, etc., right? So he published. He wrote books to the point where it's like a book a day. I mean, you can check like how many publications he has. I think it's definitely over 100 books he wrote. Not papers, books. Okay, so it's basically this guy's writing all his life mathematics. And by writing, I mean actually like going like kind of heuristically solving things, right? Like as he's writing papers. I don't think he's rewriting every time. He doesn't have time for that, right? So anyway, derivative of e to the x exponential is equal to just e to the x, and there's always math jokes about, well, I'm going to differentiate you, and the other one says, I'm not worried about that, and this guy's like, why not? I'm going to differentiate you, and this guy says, well, because I'm e to the x, because you see it kind of doesn't really change. Okay, now of course that's just kind of what they see by the result. Now it's a different idea. This is derivative, that's the slope of the tangent line of this graph, for example, at the location, and it's going to equal to that. So it's a little different what you see on the left and right. It's an input, that's an output of this derivative function. So anyway, let me now remind you this. What if we had, let me show you this, And remember, what are logs? Logarithms. Just remember what it is. Like I tell my students, even in algebra class, I say, you know what is a logarithm? There's a definition, okay? It's just basically like, what does it mean to see log? And what you do you see L sub base A of B equals to C is equivalent to, okay? It's the same thing as saying A right there to the C. So you see, the log is actually a power. C is equal to the log. So A to the C is equal to the B, okay? B is like the A to the power, the log. See, because this is a log. C is the log. And so A to the C is equal to B. This is exactly, they're identical, okay? This is just what it means. Log is the same, this right here, if you see that written, or if you see this written, there's no difference. Besides, they look different, right? And you may wonder, why am I making new stuff up when it looks different, but it's not really any different meaning? And the reason is it helps with computation, less writing, and we can actually do a lot of cool things with logarithms. But what I want to show you is, what is ln? Natural logarithm. Natural logarithm, let's say of x, is basically log, but the e is the base, that number, the Euler number, which is about 2.72 okay? There's a reason for it. There's many ways to show what the number is. For example, I'm just going to give you a little insight. E is going to equal to limit, so it's limit actually, as n goes to infinity, okay? It's just interesting if you want to look into that. 1 plus 1 over n to the n power, and so those are cool ways to find that also, okay? But anyway, let's some ideas there. I just want to show you some cool things. But I really want to get to that problem, but I'll do. So this is going to be log base e of x, okay? So we're talking about this being what? The a being the e, right? So anyway, so if you see ln, it's a natural logarithm. This is a really important number, as you can see, and sometimes we just write ln instead of log. In fact, many resources, if you think about it, have just log. Like this is actually sometimes log of x. And by log, it doesn't mean base 10. A lot of times it means base 10 if you don't see that. But a lot of times in like professional mathematical journals, papers, this log is identical to ln x. It's just so common ln that they just don't even write it. And so, log base and e or anything. So again, let me erase that because that's a little bit confusing maybe for some people. But look at this. Let me get rid of this as well. Let's go on to something like this. Let me first introduce you to, like, how about, I'm going to do, let's say, derivative of, let's say we have derivative of 2 to the x power. 2 to the x power. That's different. That's weird. That's not e to the x, right? So what you do is, we know e to the x goes to e to the x. We don't know 2 to the x goes to what, right? And by the way, let me remind you one thing. This is very important to just kind of know. And it's again, nothing is impossible to prove, like with a definition, with the depth that we've studied this. You can do this on your own. But let me just show you the derivative of the composition of functions. Like let's say f of, it's op, you can put a little circle there, op, but let me put of g of x, like a function of a function, is equal to the derivative, right? Let me actually kind of reverse the order. You can do the derivative of the inside. Let me kind of go, because usually people write f prime. Let me do g prime of the inside, right, of x, and then times, okay, f prime, okay, the derivative of the f, but of what? Of the g of x, of the function. Or, you have to put that input as this, actually. It's interesting. So that's the chain rule. Just remember that. That's very important, okay? Chain rule. And we'll use that. For example, here, watch this. So this is not e to the x. We know e to the x is to go into e to the x. Derivative of 2 to the x, well, what is that? Well, if you think about it, look at this on the side. 2 to the x, okay? I claim that it's equivalent to, okay, e to the ln of 2 to the x, okay? Now, so I'm basically saying, let me look at 2, for example. Let me actually put this down. But what is 2? What is just 2? Why is 2 equivalent to e to the ln 2? Well, let's check the definition, right? If you do this right here, by that definition of log, guess what happens? Log base e, see, like I take that, that's the a, that's the b, and that's the c. Log base e, right, of 2 is equivalent or is equal to ln of 2. But we know that's just identical. I just told you that's the definition of ln. It's log base e, right? So this, just starting by definition, then we transform it by the definition of the log, definition of ln, definition of log, right? Using that, we're going to get, now plug it in here, right? For 2 of x, we get this. And get with the powers, right? If you take a power to a power, like something to a power, you can write 2 to the x by the definition, like the property of exponents. is equal to what? That's just a e to the ln 2 times x, right? ln 2 times x, okay? Times x. So derivative of a, this is, so derivative of something, of this is what it is. Look, this derivative of, let me write that as d dx, okay? And this is not, like this, I'm giving it, I'm going to do a really much more difficult derivative, but let me just show you, start with this. Some people already know this formula, but I want to show you where it comes from. So it's derivative of e to the constant ln, that 2, that's a constant actually, times x. And if you, what you do is you say, you know what, this is going to be still going to, so first of all, what's the derivative of ln 2 times x? That's a constant times x. The constant just comes out, okay? Times the derivative of, like, the e to the x goes to e to the x, but e to the whole thing, right? That's a f prime of g, and you would get, and think about it a little bit more, the chain rule involved here. You come back with, again, ln 2 times x, okay? And that, we know what this is already. That is exactly 2 to the x. So the answer is ln 2, okay, times 2 to the x. So only difference between just copying this and getting that is that there's ln 2 coming out. Okay, now I was thinking, you know what? Give me a function, something weird, like f of x, okay? This is what I was thinking. I'm like, you know what? Even x to the x power, that's already weird. Like an exponent to an x, or like a variable to a variable power. Like that would be really strange. I mean, we know x squared, we know x 2 to the x now. What about x to the x? But let me go more involved. What about, you know, I told you logarithm is actually like a power itself. What if we take a logarithm? Yeah, let me call it ln. You know, let's do ln so we don't have to do any basis. Logarithm ln of x, so natural log of x, and I'm going to take that to a power x. Now that's going to be like, what's going on? So there are some ideas, you know, you think, oh, you know, it's similar to 2 to the x, you know, I'm going to do the, just I have the derivative of 1 over x from here. Guess what? No, that's not that easy, okay? There's a function to a function, all right? This is one function, this is another function. It doesn't work that easily. You can actually look at even this example above was kind of some, you know, had some demanding elements in it. So let me show you how I approach this problem. Let's actually do this in red. So what I say is, you know what? Let me call g of x, like let's make up a function, just the natural logarithm of x, okay? Now, what function, if I put in, let's call it h of x. So I want h of x of g of x to give me that right there, that f of x. I'm just interested, what is that h, right? That gives me back, because then I can do maybe h and g are simpler, and I can do chain rule, okay? And that's the idea. So what happens when, again, I'll tell you, like, you wouldn't probably even think of doing this until you look into this a little bit, and then you realize it's kind of failing to, you know, to directly do this. The reason I came up with this idea is because, look, I'm thinking, you know what? This is just basic calculus. This is not even like, you know, like not any, you know, partial differentiation, nothing with multivariable. Just x, ln x to the x. This is as basic as it gets sometimes in a, you know, in a calculus class. Seems like, but it's not that easy. So watch. I mean, I was like, you know, maybe like a chain rule example in one of the first chapters of a calculus book. I don't think it's that easy. So that's what I was thinking. And then what happens? Eventually, you try this, and like, if I do g, and I want this to equal to the f of x. So what? So I need h of x equals what, so that we have this right here, this composition equal to f of x, which is what? Ln x, which I was just saying, to the x power. And I want to do f prime of x later, right? But look at this. What's a way to get that? What if I do ln, what is ln x to the x power? That's actually equal to what? Okay, let me see what that is equal to. Ln x, okay, you ready? What is ln x? Ln x, okay, and this is a little tricky, let me see. So it's e, so okay, it's ln, right, of e to the x power, okay? That's for example, that's x itself, right? So we have, let me see, let me do this a little better, a little differently. So this is ln, right, of x. I was kind of, let me think, what was I thinking? So yeah, ln of x to the what? Now x itself is e to the ln x, right? You can check that again if you need to. So that's what we're doing here, okay? And that's going to give you the same result. That's ln x to the x. Now you see how there's ln x in both. What if I said, and remember, this is actually what? So this is equivalent to h of ln x, and you see there's ln x everywhere there. So if that equals to that ln x, right? What is that? Times, sorry, to the e to the ln x power. In other words, you see that we're getting this is equivalent to basically g of x to the e to the g of x power. It's to the power. Let me move it a little bit. So not multiply, of course. So let's take it to power. So you see the g of x is repeating. And what is that? So let me make a h of an input. B, see that, like that's the g, that's the input for the h of g. So the h of x will be, but that is an input x, you know, to the e to the x. And you can check again. You see h of g will be g of x e to the g of x, and that's going to give you, if g of x is ln x, it will get back that function f of x. Kind of cool, right? So let's do this. We know, also there's a natural logarithm, by the way. So derivative of ln x, which is, again, what is that? I didn't tell you this one. This is 1 over x. Okay, there's other ways to find it. There's some ways to find it using the definition of, for example, derivatives, right? But so there's L'Hopital's rule. There are different ways to do it. But watch this. This is actually derivative of the g, right? I think that we call the g, yeah, g of x. And then that's equal to 1 over x. This is something we're going to just assume we know now. This is kind of like e to the x goes to e to the x. ln x goes to 1 over x. Make sure you know that. Okay? So already, right? And so we have this. Now, what is derivative? So derivative of h of x. That's what I'm interested in. In other words, what is h prime of x, right? What's derivative, let me just write it different ways, of that x to the e to the x power? Well, let's try to do this. This is a little bit more feasible than having ln to the x, and that's what I was going for. So let's try this. Let's go ahead and do this. X to the e to the x. All right. What do we do here? Well, here, what I'm going to try to do is this. I'm going to say, you know what? X, what is that? To the e to the x, right? So, okay, let's try this. Let's find what is x. Let's find another way to write x to the e to the x. And so, x to the e to the x, right, is equal to e. You see that? To the ln x, right? That's what x is. So I'm going to rewrite that to the e to the x. Okay, that's fine. And then we have what? The property of exponents that that just a base to a power is a base to that power, the product of those powers. So it's e to the ln x times e to the x. Cool, right? Okay. What's derivative of that right there? We can do that. We can do that. So it's going to be derivative of that, of this e to the ln x times e to the x. There's a product rules there as well, right? And it's going to be, okay, let's do this. Let me do the derivative of the inside. It's a chain rule. So I'm going to do derivative of ln x times e to the x, okay? And then times just basically e to the stuff goes to e to the stuff, which is going to be, let me rewrite it one more time. It's e to the ln x, e to the x, which we know what this is. This is actually just the x to the e to the x, right? Like this is that. The circle to circle. So I'm not, because that's what we got from, this is how we got this from that. We just did some of this stuff right here, right? So you can go back to, from here, we can put that instead later. I just want to show you what it is. So look at this. Derivative of this, that's what? Derivative of ln x, that's the product rule, 1 over x, okay? Times just e to the x, copy it, plus copy ln of x, and what's that? Derivative of e to the x is e to the x, okay? So that's the product rule right there. Times just, what's that? So that's already, we took the derivative of, e to the g is e to the g. So what happens is this is going to be kind of copied to be, again, x to the e to the x, okay? And let's keep it there for now. This is actually what? This is derivative of our, this is h prime, okay? Of what? What is that? So this is h prime of just x, okay? H prime of x. Yep, h prime of x, right? So derivative of h, because is derivative of this, and we just did that. See? I just wrote, that's the same thing. So anyway, we have h prime of x. Cool, right? Let's see. Let's do it. We got this. So f prime of x is what I was going for. The derivative, in other words, of what? Of that ln x to the x power. The thing I said was a little weird, but that's the function. This is what I was going for. I want to differentiate this. It's going to be, remember, derivative of the, what was it, h of g of x. So by the chain rule, it's equal to h let's do actually g prime like I wrote it, g prime of x inside derivative times the h prime of g of x. We know h prime of x, we know g prime of x, so we got this, watch. And g of x is ln x, remember, so equals to g prime of x was 1 over x, okay, good. And what's h prime of x? Well, of g of x, let's see, what's h prime of x? It's a mess, so we're going to write it out as, what is that? 1 over x. Oh, so and this is now input, which is ln of x, right? So 1 over ln of x. Okay, you see that 1 over x there? And e, what's e to the ln x? All right, we're gonna write it. Everything x, I'm gonna put ln now. Okay. Okay. So plus there's a ln of ln x. That's weird. Well, that's what it is. It's like a base. Was a power of a power kind of thing. See? Because this is ln of x times, what is that? Times e to the, not x, but ln x, right? This. And then times what? The x itself is ln x to the e to the ln x. Okay, so e to the ln x is going to be nice. This is an x, this is an x, this is an x, right? So let's rewrite it. I'm going to remove all those. Let's see. Trying to remove these, it's a little delay here on the computation, so trying to remove these, hopefully it's not going to die on us here. Alright, 1 second. So this, we're going to remove this, and we're going to remove this, okay? There's little circles. And so let's do this. Let's see, oh, and that's it? We're done? Yeah, it seems like we're done. Like, that's it. Just make sure it looks nicer. So let's say we have 1 over x on the outside. Let's simplify this the best we can. It's 1 over ln x, right? Times, that's just x, times x, right? That's right there. Plus an ln x, oh, ln of ln x, right? Weird, like that, but it's what it is. Ln x, yep. Times, let me put that in, so it's one thing, and then times x, right? So they see the x's will cancel here, here, and there. Cool, right? Times ln x to the x power. Yeah, that's how we're expecting to get back ln x to the x power, because something to the power x is gonna, like e to the x goes to e to the x. Something to the power x goes to something back to the power x. It's just we have a lot of stuff. Oops, a lot of stuff coming out right here from it. And so, but we expected some kind of getting back ln x to the x. Some people just would copy this and like, oh, that's the answer. It's not the answer, right? So this is equal to what? Finally, x's cancel. We have. Let me write this first. So it looks kind of nicer to rewrite it. Well, I can. No, let me not do that so I don't confuse you. So let's do brackets. 1 over ln x, because x is canceled, plus ln of ln x, right? And then all that times ln x to the x power. Okay? Wow, right? Cool. This is an interesting, again, let's check it. How are we going to check it? I didn't really do that yet or anything, so let's see. But let's see how would we check this thing. Let's check. For example, I'm not sure. Like if we had a graph of ln x to the x, right? We could figure out at the point if x equals 1, that would not be impossible to do. Actually, that would be a little difficult. If x is e, like for example, if x is e, x equals e, right? For example, let's just check out what's going to happen. G of e is remember ln of e. That's a 1, right? Just remember e to the e is a 1. E to the 1 is e, and then h of e. That was what? That was remember x. So e to the e. What is it? E to the e to the e. Is that what it was? X to the x to the e to the x. Okay, that's a little weird, but we got that. All right, that's what it is. And then we had h of ln e, right? That's kind of what I was saying. So, in other words, that's h of 1, which is equivalent to, again, should be equivalent to e to the, ln of e to the what? To the x power, which is, again, this is e, which is a 1 to the e power. This is a 1. So h of 1 should be 1, which it is, right? Let's check it out. H of 1 is, what is that? Remember, it's x, so 1, to the e to the 1. Yeah, it's working, okay? So it's still 1, because 1 anything is 1. 1 of the e is 1. Okay? So I'm just messing around a little bit here, but look at this. What are we getting for derivative? Like, let's say for x equals 1. By the way, if x equals 1, so there's this point, like for example, 1 comma h of 1, in other words, 1, 1 on graph of h to the x. Just having some fun here, but we did it already, right? Which hopefully it's making some sense. And so that and derivative of there, the slope of that tangent line there is, let's see, is h prime of, I put x equals, wow, I put x equals e in, right? So, oops, let me ln I put an e in, right? And I got the point, what if I put an e in? If I get, look at this, if I put e in, I'll get e to the e to the e, right? 1 second. If I put 1, well, so what is it? H of 1, right? That's so the point 1 has a h value of 1. So, right? H of 1, yeah, h of 1, sorry, h of 1 is not e, that's that e, that would be putting e in. H of 1 is, that's, I don't want to do that, I want to do h of 1, and h of 1 is 1, sorry, okay, that's what we did. So the derivative there is, see, there's a problem, it's undefined, okay, and I'll show you why. Like, let's see the function even, let's see, because, let's see what happens. H prime of 1 is equal to, you'll see what happens. So it's 1 over, let's plug this in. Ln of 1 is 0. But you see you're going to have an ln of a 0 there, and that's going to be undefined. So we're going to have ln of 1 there, and da-da-da-da-da. So undefined. Ln of 0 is undefined. Okay, so we have undefined there. And then let's try h, so at point, what is that? E to the e to the e. Let's do that. So, I mean, I don't know, like that's a big y value, right? And let's quickly do that. H prime of e, because I think we can find this one at least, is let's see what that said. 1 over ln x, so 1 over ln e is just a 1 over 1. 1 over 1 plus, remember I said ln of ln, so ln, what's ln of e? It's 1. That's a 0, going to be a 0. Times, and then we had ln of e, right, to the power e. Okay, and that's going to be, that's a 1. So it's 1 plus 0 times 1 to the power e equals to just 1. Okay, cool. So that's the derivative there, interestingly enough. So it's increasing there. For example, again, this is if we did it correctly. That should be the answer there. We can write it maybe a little differently also, but cool. All right, everybody. Hopefully this was interesting. Again, this is derivative of this, unless we made some mistake and forgot to divide by something. But I think it's right. All right. Have a good day, everyone.